is the phase diagram? Phase, already you know, the material phase, material state. Okay, at which condition the material is basically, and what the kind of condition? The condition is their appearance. Either it is a solid or liquid or gases. Okay, that is your phase. Okay, so how the phase diagram? What is the phase diagram? First, we need to understand, and then we will draw how the phase diagram is being drawn. Okay, the solidification of the metal alloys is clearly indicate by means of the phase diagram. Okay, also known as equilibrium or constituent diagram. Why? Equilibrium means, I mean, whenever the state you are in a condition to define the properties of that particular material is known as your state, and only at equilibrium you can define the properties. Okay, otherwise you cannot draw the properties. Okay, as I know that you have already read these kind of things in your thermodynamics. Okay, so thermodynamics is very similar kind of definitions. So in the phase diagram, the graphical representation of the changes in the state due to the variation in the concentration and temperature enables the phase content of the alloy to be determined at any temperature and composition. So what you need to know first, I mean, it's a basically graphical representation of the changes in the state. State means the point, the position in which you can define the property. So basically, you are basically having a different state means different properties. Properties means different properties values. Okay, suppose, I mean, temperature is a property, right? But temperature having a different value at different state. Okay, so that is known as your state. I mean, the value, as you can see in the previous diagram. Yeah, this A to B. Okay, so if we you cannot have the any idea, but if we talk about the A, so A you can define what the temperature is. B you can define what the temperature is. So temperature is a property, and you can, if you are able to define or you are able to calculate the value of that particular property, then it means you are having a state. So only on a state you can define the properties or you can calculate the properties. Okay, so and if you are able to calculate the properties, it means the system is in equilibrium, because without an equilibrium you cannot the property any properties values. Okay, so try to understand what is the properties, what is uh, the equilibrium. Okay, so what we need to know, I mean, in the state means you are able to define the or you are able to calculate the properties value. Okay, so variation in concentration, or concentration means, I mean, how much volume fraction the two metals are there. Suppose you have the two metals, binary solution A and B. So at particular value or particular state, how much uh, the volume fraction of A is present, and how much fraction of volume by B is present there. Suppose, I mean, you cannot exceed the mixture of, I mean, anything of one. One means the 100%. So if you have a solution that is not 100%, if 10% of is from A, then it definitely means 90% from the B. Okay. So at particular state, you would have the different concentration. Okay. If it is, kind of 91, then it will be like 9. Okay. So they will be varying the state. So at every state, you need to define the concentration of A and concentration of B. That's why we have written here the variation in concentration and temperature enables. Temperature means at what temperature you are basically calculating the concentrations. Okay, and you are basically having the state. Okay, the phase content of the any alloys to be determined. So I mean, at what concentration and what temperature you have defined the two things. Suppose here you have two things. Suppose you have keep the temperature here, and here you have kept concentration, right? So you are having x-axis and y-axis. Now if suppose, like, I mean, anything, your graph is like this. Okay, so at particular this point you could have your temperature here and concentration here. According to that, you can define what the phases that occur at that particular point. That is basically phase. So corresponding to the temperature, you need to calculate, I mean, you need to first calculate the concentration. So when you are having the temperature and concentration, according to that you can easily track your the phases, because easily, I mean, we know how to read the graph. The graph is come to the from the x-axis and y-axis, and where they have, I mean, both intersect each other, that point you are having the state, and that particular point will define you whether you are in which phase, either liquid, gases, or solid. That but in the case of current study or current topic that we are discussing, we are not discussing the solids, sorry, gases. We are having only the liquid and solids. Because in solid solution we are here. Okay, so we can determine the composition, determine at any temperature and compositions. So what is the benefit of the phase diagram? They enable the phases transformation while heating or cooling. So if you are heating the system, or you are cooling down the system, how they are transforming, how the phases they are basically crossing, and what at particular temperature and concentration, what is the value of uh, you know so what is the state, or what is the condition, or what is the phase of that particular system is there, you can easily determine under the equilibrium condition, which is very obvious, otherwise you cannot calculate anything. Okay, so when all the process in the given systems are reversible. Okay, what reversible means? It means, I mean, if suppose you were here at point E, okay, and now you come here at B. Okay, I mean, anything. Suppose you are as a human being or any system, you can consider about. So if you have come here the same way, and you have, suppose you have consumed suppose 5 liter of water, okay, or anything. I mean, the energy that you have required. Suppose petrol, okay, the bike that you have driven, okay. So whatever the energy that you consume, if you reverse the same way, same path B to A, okay, the same thing, if you can reverse, means the amount of heat that you have taken, that if you released by going in the same way, then it is known as the reversible process. Do you can think about, I mean, how it could be possible if I'm going 5 kilometers ahead by consuming the 1 liter of petrol, and then if we will reverse the same way, how could we can reflect, or we can produce same liter of the petrol, which is not possible. Yeah, obviously it is not possible, but this is a condition. This is known as your reversible. So going with the bike, consuming the petrol is cannot never be as a reversible process. Okay, so this is the idea how you can think, how you can differentiate between the reversible and irreversible. I mean, as we are growing, okay, whatever the day that we have left tomorrow, sorry, yesterday, and whatever the time that we have already enjoyed, or whatever the time that we have lived in yesterday, could we reverse them? No. So the growing of a human being is also known as the irreversible process, the process which you can reverse. Okay, and reverse is a condition. What condition? That whatever the things that you have consumed to come here at the particular point, you are basically rejecting the same kind of the things to reverse back. So, I mean, in most of the things are not reversible. But why we are studying? Because the reversible is a condition, it's an assumptions. Though there is no perfect reversible process in this world. Okay, but still we are studying because we have assumptions that our system, our things is behaving like a reversible, though they are not in a reversible. But why we are studying? Suppose you have here in the case of same here in case of A to B. You have reached here. Okay. Suppose you have lost, or you have come across to the friction. Okay. And I mean, whatever the friction that you have encountered, could we reverse them? No. So taking into the account to the your system, your friction into account, though you have, suppose you have a efficiency of suppose 60%, right? So in practical life, you would be able to understand it's mean the real life process, if based on the same process that we have calculated 60%, that would always be less than of 60%. This is the idea basically. So whatever the calculation that we do in our class, that would be of your highest values. So in practical life, you would be having the less value. So this is basically a kind of benchmark that you could think about. We cannot run more than that. Okay, that's why we assume the reversible process. So reversible process means whatever the process that you are facing, going into that, they can reverse the path. Okay, by reversing. I mean, if they have taken the heat, in case of we take the example of the heat. So whatever the amount of the heat they have taken from to reach A to B, the system will reject the same amount of heat if we reverse the path B to A. Okay, That is very not obvious. Okay, but this is the idea about the reversible process. Okay, the system must be reversible because this is basically reversible means they are behaving like a reversible, but though it is not possible. And so why we are studying, because and suppose you have taken you have provide the heat to any system that is in a solid form. Now they have converted into the liquid form, right? So if you have to provide the heat, they have got a temperature high, and then at the critical point when they have crossed, they have converted into a liquid. So what the idea behind the reversible? If we will extract the heat as we have seen in the cooling curve. So when we are extracting the heat from the same, then they will cool down, and at the after some time they will reach at the same state. Okay, same conditions. This is known as reversible. But though they are not perfectly, but some kind of the heats being lost, some kind of the as we know that, I mean, there is a stress concentration kind of thing. I mean, there is some assumption of the heat which is being stored inside the materials. That's why it is not perfectly reversible, but almost it is close to the reversible. That's why we study. Okay. So what are the term that we are that I'm defining more, that you could have the idea, or you can remember them. So better understanding of your a subject in a broad sense. Okay. So difference so reversible. So this means that the changes taking place in the system as a result of the process proceeding in one direction are fully compensated by the changes due to the reversible of the process in the system. All the phases diagram have the temperature as a vertical scale or ordinate. I mean, here as you can see, the y-axis as known as the ordinate, and the percentage of the composition by weight as a horizontal scale, which is known as abscissa. Abscissa means, which is x-axis is known as abscissa. So what you need to define in a phase diagram. So at the x-axis or abscissa, you are having the composition percentage by weight. Okay, not by volume, by weight. Okay, but and if you talk about the y-axis, then we have the temperature in centigrade or Kelvin. Okay, so depend on your condition. Most of the time, it is given in your temperature, centigrade. Okay, but you could have in Kelvin as well. That doesn't affect your uh, diagram. Okay, so phase diagrams are of three types. What is a single component or unitary phase diagram? Second one is component or binary phase diagram. Third one is three component or tertiary phase diagram. So single phase diagram means a single component means you are having the pure metal, pure element. Nothing else is there. Suppose this is a very good example of water. Okay, so if you are having the phase diagram of the water, it is the single component. Okay, so single component means only one component or a phase is there. But if we talk about the two components, means that you are binary phase. And if we have the three component, then we have a tertiary phase. Okay.